If you push it, then you can share the screen of your tablet.
Well, I'm going down now, so it doesn't do much. Let me do it.
It pops up if you go down. You have to go down to the
bottom line.
Bottom line, and then it pops up.
Well, I'm on the bottom line now. It doesn't do a thing.
In the middle, there's a green bottom, which says like screen. I don't know what it says in English.
Oh, now, okay. Now let's see. Now I'm on. I see myself, and my presentation, and
Professor Grätzel, you have to click on the share screen button, and then you can choose which screen you will share, and then you have click again share.
Okay. Okay, yeah, that's what we were practicing, but okay.
No, it didn't work perfectly fine before.
Oh, here, I click on my lecture.
Mm-hmm. Oh, yeah.
It's coming. Yeah.
And it's now shared?
Yes, it is.
Okay.
And then you have to click the presentation button.
Yeah, of course.
Of your PowerPoint.
Yeah.
And then we are fine.
Course.
Yeah, perfect.
That happens all the time. Now we lost about 5 minutes. Sorry. Start all over again. Okay. So what I was telling you was that the journey which we will take together is starting from our inspiration and the example of Mother Nature, the photosynthetic life-sustaining process, and out of this, we developed this mesoscopic or a solar cell or molecular photovoltaic cell. Yeah, and then this cell evolved, and today we have applications like this green wall that is providing electric power for the car that is behind. But also, as Professor Herke said, in 2009, a new evolution started, and that was with the development of perovskites that replaced the sensitizer. First nanocrystals, then films. And today, I mean, this started with a 3% device, very unstable. And today, the efficiencies are up at 25.6%. Just a couple of days ago, new record. So beating the market leader, polycrystalline silicon. And so let's get started. And so first, I will talk about our motivation, our inspiration, research approach. Then molecular photovoltaic, the rise of perovskite solar cell, and the applications. You all will share my concerns about the environment, pollution, and climate change. I don't think I have to dwell on this slide. And so this was really a driver for our research. We tried to make contribution. And if you look at the analysis that came out from Shell Corporation, oil company, the Sky scenario asked for a 200-fold increase in photovoltaic power in the next 30 years. So that's a real challenge. And we need that. We need to replace the, as you can see, the pie chart here, the dark area, that's the fossil fuels. They go down and the renewables have to go up. But then the pie is also growing. So this makes a factor of 200 for the solar PV. And that's a challenge. So how can we meet that challenge? And silicon is growing up, but the increase is not enough. It's about 100 gigawatt installed every year. That's peak power. But we need at least 20 terawatts. So at this rate, we would take 200 years to get to this kind of capacity. And so we need new ideas, new developments to come to the aid of the silicon. They're doing a very good job, I should say. And so the plant is already at 90 terawatts. Remember, we're presently consuming 18 terawatts. That's a power consumption. And so that means, I mean, plant, this is stored power. It's storage happening all the time. It's not energy, it's power. And so that beats our present consumption by a factor of 5. Then the plant use a molecular absorber, not a p-n junction. And it's a fascinating process. We won't go into the details, but it is correct that the light is absorbed by a molecule, a dye, chlorophyll, and that sensitizer produces electrons and positive charges in the leaf. Now, they're not coming in, you don't get electrocuted if you touch a leaf. Why not? Well, these charges are very quickly consumed in electrochemical reactions, the reduction of CO2 and the oxidation of water. And so, so the molecular photovoltaic approach, it goes away from the p-n junction, and in the dye-sensitized system, we use a molecular dye. So the dye gets excited, the electron is injected in an oxide with a large band gap like Ti2, and that's a charge separation. You have a negative charge in one material, that is the oxide that carries the electron, and we have the positive charge on the dye. So now we have collect those charges, and that makes a photovoltaic device. And so I will just start that in this reaction for you. So light comes in, electrons get excited, they get injected, collected, they have to be taken back to the dye. So we need a redox couple or a whole conductor that takes the electron from the back contact back to the dye. Otherwise, we deplete the dye in no time. And so all turns around for a while, for many years, we've been fiddling with this scheme, how to optimize it and how to get the efficiencies and stabilities up. And at the end, we developed a solid state device, which has become, in a way, the basis for the perovskite, the present perovskite development. And today, I mean, when I look at our Nature paper in 1998, for the solid state dye-sensitized cell, and compare this to the best perovskite cells, they still use the same kind of scenario, same architecture, almost the same materials. But I mean, the sensitization was known at the time when we started. It's just the efficiencies were very low, and we can see on the scale, current scale, these are nanoamps current, but a photovoltaic cell should evolve milliamps. So we were orders away from what should be delivered. And actually, when we started to work on this, our colleagues said, "You're wasting your time. This is a hopeless effort because it's never going to work for X, Y reasons." And but we came from a different angle. We were working on those nanocrystalline films. I'm sorry, and so we had done a lot of fundamental research on these oxide nanocrystals, sensitizing them, understanding kinetics. This was all curiosity driven, and until we decided to try a dye-sensitized experiment, and we found that the commons, I mean, the photons went up by a factor between 1 and 10,000. It was not a factor of 2, it was a huge effect. And with this disordered three-dimensional network, we could produce these high currents. And so that was a breakthrough and a new paradigm in the photovoltaic field, which until then had lived from just a physical picture of p-n junctions. And so here, just in a nutshell, so we assemble those particles. They are sintered together and assembled on a conductive glass support. Then we dip in a dye solution. Here's one of our ruthenium dyes, and it has the anchoring groups that will attach it spontaneously by a monolayer formation, self-assembled monolayer formation onto those particles, and that becomes a highly colored film. Why? Well, the surface area is so huge of these particle films. It's about 1,000 to 2,000 times the projected geometric area. And so you get a lot of light absorption. And the amazing thing was that we also could collect the electrons that were injected. So the recombination reaction between the electrons and the oxidized dye were much slower than the collection and injection process. That was something people would not believe, but that's the interfacial reactions are much slower. So we collect these charges and get high electric currents. And so the first paper was the first landmark paper. We had published quite a few before, published in Nature, 1991, and that has been cited over 25,000 times. And so it's one of the 100 papers the most cited in science as a whole. And so why was it cited so much? Well, because the concept was new. And you see, this doesn't look like a PV cell. It looks like a tainted glass. But in fact, it collects a photon from both sides, the back and the front. And you can see the fan turning even in diffuse light conditions. And so, as I said, it became almost a brag about it, but it's amazing that a paper like that got so many citations. And this is Brian, my co-author, at the conference in Uppsala a few years ago. And so today, there's a lot of chemistry going on, these dyes being tailored so that they have a donor acceptor group and connected through a pipe bridge or a chromophore. And that makes very good progress, and efficiencies are still rising for dye-sensitized solar cells. And so it becomes really an area of synthetic organic chemistry and also photochemistry. And that is supported by computational studies. They help tremendously in the design, conceptual design of certain dye molecules, certain functional groups. Here's an example where we show that we can get a green color with this porphyrin donor function. The acceptor has a carboxylate which hooks it onto the titanium oxide surface. And so that's the right geometry because you want the electrons to flow from top to bottom when you excite the dye. And here you see some electron density mapping from TD-DFT calculations. And you can see in the ground state the blue distribution of charge, and this shifts towards the carboxylate as you excite the sensitizer. And so this is a real fun game, and we got very low charge separation. And this dye is also applied now in some practical devices. I give a few examples here. It's just that people like it a lot as a green. It mimics the plant. It looks green, and it has a high performance. And other projects that have been realized. So the scale-up has happened with the dye-sensitized solar cell. And we have mainly those glass applications, the glazing application. And we have another application, which is in the ambient light harvesting. That is one feature that is very, very nice of dye-sensitized solar cells. Here you get some of those new structures. You see the cyanoacrylate binding group and bisphenol and benzothiazole. This is the acceptor part and the donor, and the copper is copper 1, copper 2 complex, the bipyridine complex. They turn out to be a real good redox mediator. They can regenerate the dye at very minor loss, and they give a high voltage. So we were able to get very good performance. Actually, this logo here, this a photovoltaic active film, and it beats gallium arsenide. It is printable. And so here's a comparison we published not long ago. This on ambient light, the conversion efficiencies are very, very high. And this has also led to practical applications by a variety of companies. I'm just mentioning here some of the from Swedish, very famous Swedish company that has now commercial applications on black surfaces are all dye-sensitized films, and they provide the battery, they provide the power to run those electronic equipments. The battery is just a backup. It's not needed for running these devices. So this gives you the flavor where we are with the dye-sensitized cells. But really, what we want to talk about today as well is the evolution, this very exciting evolution since 2009, and this on the left you see the beauty of a dye-sensitized solar cell. It's a Sony realization, and here you see that black perovskite cell. But it's a very powerful converter, and we know perovskites, mainly oxide perovskites, but these are halide perovskites, and there's a variety. You have the inorganic ones, cesium and cesium lead or cesium tin, and so there's a variety of choices. It's just these ions have to have the right size to make a perovskite. There's a rule called the Goldschmidt tolerance factor, and that has to have certain values. I'll show you a slide in a minute. So lots of interesting properties, and it's amazing that they really only came out through the work of Tomi Asaka, who used those nanoparticles of perovskite in a dye-sensitized device, the first time in 2009. And I should also mention these materials have a special properties. The conduction and valence bands are antibonding, and that's very unusual. Normally the valence bands bonding and the conduction bands antibonding in semiconductors. But this unusual electronic structure makes it a material that has very few defects in the band gap. So that I mentioned that in passing. And so this is the first paper by Tomi Asaka. I remember I was a referee on this paper, and so these black dots, these are the sensitizers, and it was published in JACS. And then 2 years happened and nothing. Nobody took note. And then Namgyu Park, he published a paper in nanoscale, which picked that up and improved the stability and performance. And but then the real issue was with these electrolytes. Perovskites are ionic crystals. They dissolve in polar solvents. So it was not a good idea to use these polar electrolyte solvents. And so then the whole conductor changed the whole picture. So the electrolyte was replaced by whole conductor. Here are two papers that came out in 2012. Namgyu Park had asked us to join him. Why is that? Well, because we had worked on this solid state version and published paper like 10 years earlier in Nature, and where we had shown that we can get high efficiencies by just replacing the electrolyte by this whole conductor, which is still being used today, the spiral meotat, spiral-connected arylamine. And so here the structure is such that you have, again, the dye-sensitized oxides, but then they're in contact with a whole conductor, and the whole conductor takes the positive charge to the back contact, and this regenerates the dye. And so yeah, then in year 2012, as I said, there was these two papers, and two other papers appeared. One by Professor Kanatsidis in Nature, and he was a dye-sensitized cell, a real dye-sensitized with the perovskite as a whole conductor. He showed sensitization effects. And so, and then it was, it took a whole, this started a whole revolution in a way. And that this is a paper we published soon after in Nature. And today, you can see this is the curve. We're starting with efficiency of 3.8%. This is Tomi Asaka's work. And then 2012, we get close to 10%. And this point is actually now it's old. It is already superseded by the new measurement of 25.6 confirmed. These are measurements that have been certified. And also note that the number of publications today is somewhere around 15,000 or even higher. So incredible number of papers coming out. But these systems are complex. They have complexity of composition, and you have the also the structural complexity. There are 2-dimensional perovskites, 3-dimensional perovskites, and so compare this to silicon. It's a much more complex scientific problem. And I just mentioned the crystal phase stability issues. For example, if you like to use formamidinium lead iodide, which has the best optical electronic properties, then you would have it in the perovskite phase, which is the alpha phase. But below 170 Kelvin, 170 Celsius, it goes over in the delta phase, which is totally inactive. And it's the yellow phase. And the same for cesium, then the transitions even at higher temperature. So, so a lot of people got stuck with what they call MAPI, methyl ammonium lead iodide. But that's not the best material. It's FAPI would be better. And so it became as an important discovery, and something that was directing research for since then, I have to say, was that discovery with Joachim Meyer and his group from Stuttgart at the Max Planck Institute for Solid State Research, that you could stabilize the formamidinium just by mixing methyl ammonium iodides. So when you mix that, you still get the band gap is shifted to longer wavelengths. That's good. We want to collect more sunlight, and also the optical response is improved. So yeah, and so this was then we and others found that the cesium also, the cesium lead iodide is unstable, but if you, or the formamidinium, if you use cesium with formamidinium, you stabilize one unstable material by another unstable material. In other words, cesium likes to form yellow phase at room temperature, formamidinium also yellow. But if you mix them, just grind them in a mortar, they turn black and make the perovskite. And so this has been analyzed, and statistical mechanics has been used to explain these conversion reactions. And but then kind of inflation happened, triple cation and quadruple cation. And so people studied the more complex system. But at the moment, actually, today, the trend has inverted because the highest efficiencies are obtained with formamidinium-rich formulations. That's a fact. And so the more formamidinium you have in your system, the better your efficiency. And so that has led to great efforts to stabilize. As I mentioned, we found with methyl ammonium we can stabilize, but there are other ways to stabilize the formamidinium. And so I just mentioned to you today, where do we stand? We are back to using formamidinium methyl ammonium. Here is a 5% methyl ammonium, which is very little. And still, these are extremely stable. The voltage, 1.2 volts, very close to the Shockley-Queisser limit. And that's confirmed by the fact that you get electroluminescence when you drive these cells with the external voltage, they actually emit light. And also the ideality factor. We are comparing here black and red curves. And so the red curves, there is a trick, a small amount of molecular modulator. So that's really what changes the game, because defects, always defects at interfaces. And how can you take care of the defects? If you do, the perovskite will deliver very high efficiencies. Here, our certified efficiency is 25.2. In the lab, we already have obtained higher efficiency. But I should mention this work is done in collaboration with my colleague, Anders Schackfeld, and his assistant, Hai-Ju Lu, and also the UNIS, the Korean Institute of Science, in Industrial Science and Technology, Ulsan Institute of Industrial Science and Technology. So this is a collaboration which has produced that result. And so, yeah, efficiency is not enough. We have for photovoltaics, you need stable and stable behavior on cost. And so the stability is still, still being improved for perovskites. It's not bad. I mean, it has been going up considerably, and but we need to do more experiments, make sure in outdoor conditions that they will last for 25 years. And so, for example, one thing that came up that was really disturbing was that new photo effect that was ignored. In other words, Professor Meyer discovered, so we had joint paper with him in Nature Materials recently, that under light, the ionic conductivity of these ionic crystals increases by more than 100 times. I mean, it's a huge effect, and it contributes to instability. And so one has to get this under control. And there are always new things popping up with perovskites. So we need to do more research, definitely, to fully understand these complex systems. Here we have a promising experiment where we replace the spiro organic coal conductor with copper thiocyanate. And this was, can also see the simplicity of the cell structure. This is glass. Here comes the meso Ti2. And then here's the perovskite. So still mesoscopic Ti2 films. And then this is the gold on top and copper thiocyanate hole conductor. And by protecting the gold, so here you see the structure again. This is our glass, then comes the Ti2 infiltrated nanocrystals, and then the perovskite itself, the capping layer, and then the hole conductor and gold. So very, very thin layer, much thinner than silicon photovoltaics. They use a 200 micrometer, not 200 nanometer. Okay, so that's a huge difference, and so you need very little material to get to these high efficiencies. And see also here we were able to get 1,000 hours continuous elevation at full sun at 60 degrees. That's a standard test condition, and it's reassuring that you can reach this. Very often instability comes from ambient moisture or the contacts degrading. So all of this is not always to blame on the perovskite. And so yeah, let me perhaps end my talk and talk to you about some applications. Here is an article which I thought was very interesting. It came out this year, and it asked the question: is the perovskite solar cells, are they heroes, villains, or just plain fantasy? Okay, and so the question is really: is there a role for perovskite solar cells to become a large-scale provider of renewable energy in the future? And this person is from the industrial world. He knows the photovoltaics, and he makes a case. He makes a case that we need a new technology because the silicon modules will not be able to deliver this terawatt power that we need in the next 30 years. That's his opinion. And so this is a rather positive standpoint. So rather hero than villain, I would say, okay, at this stage. And yeah, and so there have been, I should mention, there's also production. Various companies in China are now producing modules, and one company in Hangzhou has announced to produce 200,000 square meter before the end of the year. So we will see. I mean, they shown us these modules and they look promising. We'll see how they do outdoors and outdoor testing. And yeah, and also, I mean, the perovskites are a very good voltage source for water splitting and CO2 reduction. So Professor Herkes mentioned that this is actually our one of our sidelines of research. Well, it becomes our actual major research effort. And so we are interested in solar fuel production because, I mean, electricity cannot always be digested by the grid. and then the price goes down of electricity, and it becomes commercially unviable. So for example, here last year we published a paper in Joule, but where we used the perovskite silicon tandem cell. And I should mention there's a company in Germany, Oxford PV, that developed such tandems. We use a tandem which was developed with our colleague Christoph Ballev from the EPFL. And so here the perovskite silicon, if you put them in a tandem, they develop 1.7 volts at full sunlight. That's just what you need to electrolyze water. So it's a perfect match. Don't have to do any twisting. And so that's really hard to beat, because at that time when we published that work, we used the perovskite solar cell that was far from being at the top of efficiency. It may have been 21%. As I mentioned to you today, we have 25% cell. But still, we did get this efficiency of 18.7%. So 18.7, here it says achievement of 18.7 solar-driven water splitting. That means 18.7 solar to chemical, solar energy to chemical energy stored in hydrogen. And this will certainly be going up further. And it's a relatively simple system. I should also mention our compatriot Nicholas Hayek, who actually was the CEO of Swatch Group and the inventor of the Swatch. Look at his left arm. You can see right away that he is in the watch business. But not only, he was a visionary who had in mind that this watch should be electric car. Yeah, and today, actually, my brother just bought an electric Swatch car. So his dreams have become reality. But he also had the idea to decentralize fuel generation. So you have the photovoltaic panels, and then you have the electrochemical converter that can make CO or hydrogen, and in the water splitting, the simplest reaction is hydrogen oxygen. You can drive a hydrogen car, and so that's actually also become a reality. And today I have driven a hydrogen car. It's very convenient, and there's a very long cruising range, fast charging, refueling time. Well, when you go to the pump, I mean, the outlet has a pressure of 1,000 atmospheres. so it's great, but this is entirely safe. It's well controlled. And I should mention to you that several years ago, I was contacted by Bill Gates, and he asked me to visit him. So I hopped on the plane, and he wanted to have my opinion on solar fuels. And I gave him one of our backpacks. This is a dye-sensitized solar cell. This is a dye-sensitized keyboard. And we really had a very nice conversation. And Nate Lewis was the second scientist in the conversation. He is a very, very sharp person who, at one point he said to me, "Michael, can you explain to me the Fermi level splitting?" I said, "Oh, wow." I said, "You really want me to go into details?" Yes. So it was impressive. And not so long ago, he visited the folks in Pasadena at Caltech. This is Nate Lewis, the leader of the team. And they set up a $1 billion fund for developing solar fuels. And so it's a real interesting development. So with that, I think I should stop. And now I have to give credit to, first of all, the EPFL that is hosting our research group. You see the beauty of the Alps behind and Lake Geneva. Here's our laboratory in the corner. Our funding agency, European funding, Swiss funding, some prize funding. And And so, yeah, this has helped us to develop our research and some other actions that some companies supported our research. And here comes some acknowledgement. Anna Scharkfeld is my colleague here. Recently, he was appointed president of Uppsala University. So that's a real steep promotion, and he will leave at the end of the year. But certainly we'll keep in touch with him. And this Professor May already showed him to you. This is our group photo on a gloomy day in the fall last year. And you can find us on this website, and you can find more pictures, every group member. But look how much better it looks in the mountains. So in Switzerland, you have to ski because you get a completely different world up there. And so see here, I'm standing with my skis just at the cliff, but fascinating. And we have a beautiful nature and should conserve it. Thank you for your attention.
So thank you for your exciting lecture. I think we have time for a few questions. And unfortunately, the award ceremony is a bit different from recent years, and it's online, so we have online questions. There's a question from Dr. Baha Tosun Erkan, who's asking, what's your recommendation of encapsulation materials for perovskite? I think he's hinting at the sensitivity towards moisture.
Yeah. This has been a real pain. I mean, we have struggled with that, and especially for small cells. But fortunately, there is an Australian group in New South Wales. They published a paper in Science recently where they just use the butyl, so polyisobutylene that's we use for window. It's called butyl rubber. And if you look at your window, if you have double glaze, you see some kind of a black ceiling. That's the same material, okay? And I had recommended I always said we should look for that material, and they did. And indeed, I mean, this seems to be the way to get also for small cells easy. You just wrap these cells into the polymer and then heat it up a little bit, and that makes a hermetic seal. And your windows also, they last for 30 years, no problem. There's no gas coming out or going in, and it shows the performance. So my answer to this colleague is, yeah, just write me an email. I can send you the reference for the science paper. It's out just a few months ago.
Yeah. Are there further questions? May I ask a question? You have impressively improved the efficiency in converting light to electricity. And in the beginning, everybody was improving the dyes. And then perovskite came in as a game changer. How systematic is improvement of dye-sensitized or perovskite solar cells? And what part is chemistry, and how much do the device makers contribute to increasing sensitivity, stability, and so on?
Yeah, so I have Lukas Pfeiffer. He just joined us on Havinga's group. He's leading together with Yuan Liu, my organic group. I always had an organic chemistry section in our, although I'm a physical chemist, we need organic chemists because the structure is getting more sophisticated in the dye-sensitized field. You also need to develop synthesis methods that are not too expensive, and also the spectral response. So you look at the dyes which I showed you, the ones that give these very high efficiencies in ambient light. They actually, the structure is not our idea. It comes from Shanghai, from Professor Tian's group. He had this idea to have a donor and a very strong acceptor, and then another linker and another acceptor. So the the computational efforts are also very important. And you can not only model the dye itself, and today's programs and codes are allowed to, with 0.1 EV accuracy, to predict what the absorption maxima are. And also, of course, the charge distribution, the HOMO-LUMO levels. So it's without doing computational chemistry, you're left in the dark. And so we are also working with a colleague here, Professor Ursula Röttlisberger. She does computational chemistry, but we're also doing our own calculation. And so that's so we're doing a fair amount of chemistry. And now comes for example, the copper electrolytes. These are, we also had to work on the ligand structure, and there was a surprise phenomenon. But I might mention that the fastest redox enzyme is P450 in the plant, and that's a copper 1,2 copper. It's a histidine ligand, and nature can achieve exchange rate constants that are still 1,000 times higher than our best copper bipyridine complex. So we still have a way to go, and we are trying, of course, to mimic these peptide structures to get even faster exchange, and solid state, get those, use peptides, if you like, to transport charge, not solvent containing system. These are really exciting things going on in the DSC, and they pay off because efficiencies have been improving, and we are regularly certifying our DSC efficiencies. It's true that the perovskites, they are exceptional in their steep rise, but you need, the chemistry is also is very important, and it's clear that the fact that we worked with solid state chemists from the Max Planck, and we also did lots of theoretical modeling and including collaboration here with our colleagues that developed the quantum espresso program. This field requires to collaborate, is interdisciplinary, and if somebody only works on one aspect, he will not get to the leadership of the field, I would say.
Pleased to hear that organic chemistry is important and theoretical chemistry is important.
Yeah,
So,
yeah, essential.
Questions seems not to be the case. As I mentioned, the award ceremony is a bit different from recent years because of Corona restrictions. Unfortunately, I cannot present you the Diels Planck medal in person, but I can show it to you.
Okay, let's try to do that. So should I?
Yeah, it's reflecting. There's Diels and Planck.
Yeah, I see it now. Great. Yeah.
Fortunately, we did it on your competitive material. It's made from a silicon wafer.
Okay. Okay. Well, that's great. I mean, I love silicon. As I said, there are no tandem systems.
So there was some chromium sputtered on top, 10 micrometers and nanometers, and then a gold was sputtered, and it was etched with chromium acid. So also this was interdisciplinary. So we also have a document. Unfortunately, I cannot hand it over, but we will send you the medal and the document by surface mail.
It's very kind of you. As I said, it's a big honor, and I thank you for inviting me to this lecture, and I thank all of you for listening.
Yeah. It's a pity we cannot meet each other in person and invite you for dinner. I hope the situation will improve and we can catch up on that. Thanks again for your lecture and accepting our award invitation.
Thank you, and have a good ongoing afternoon.
Yeah. So to all participants, please don't leave. We continue. We still have a lecture. So I hand over to the next session chair, Bernd Streme, and he will announce the last plenary lecture. Bernd, it's
Yes.
your turn.
Joseph, are you available? Could you turn on your microphone? Okay, thank you very much. It's a big pleasure for me to announce well-known photochemistry, Professor Joseph Jakshi. He comes from